Okay, first let me clarify the confusion we were having last time where I was trying to derive the softmax delta in the neuron, and we were having some difficulty, right? So anyway, once I left the class, I drew it nicely. And like I said, I had done it before, but you know, sometimes if you don't take a look at something for a while, you miss a small thing. And it's tricky. The softmax derivation is tricky because you know, normally, as we have discussed, so see, if we have, let's say, a couple of systems feeding one to another, right? Let's say here's the loss, here's some kind of a loss function, here's A, here's Y. Okay, here's some other system, let's say the input is P, input is Q, right? Okay, if we wanted to, for example, compute partial L over partial Q, as you guys already know, we simply, you know, make a chain rule. We'll go partial L over partial A times partial A over partial P times partial P over partial Q. And if we just step by step solve these, we'll be able to get the answer, right? Okay, however, what if our system is not, you know, a linear, meaning, you know, a sequence of blocks like I showed you over here? What if it is something like, let's say, here's something, these feed to the loss as an example, right? Then this goes over here, this feeds over here, this feeds over here. So suppose I put P, Q, this Q as well. Okay, and let's say this is R, S, L, K. So suppose this is some Z, right? So what if we wanted to compute, let's say, partial L over partial Z? Okay, so now there are multiple paths involved. As you can see, there's a path involved over here, right? There's a path involved over here. So now we have to accumulate the gradient. So it will be, for example, partial L. So if we take a look at the top red path, partial L over partial R times partial R over partial Q times partial Q over partial P times partial P over partial Z, right? Then what should we do for the bottom path? Multiply it further or add it? Plus, right? So then it will be partial L over partial S plus partial, so multiplied by partial S over partial P, and sorry, then there's Q over here, this Q over here. Q times partial Q over partial P times partial P over Z, partial Z. And then we can individually compute those and find it, right? So with the softmax, that was the issue. There were two issues. One issue was picking the variables properly, okay? The other issue was, see, for example, if you take a look at the softmax function, right? Okay, so let's say here's a neuron. We produced the sum. Okay, then we pass it through, remember we need to do e raised power s over summation of e raised power s for all the others. Okay, so then I was calling it s, I was calling this s, so the s has gotten confusing. Also, if you take a look over here, if you take a look at the bottom term, okay, it's really accumulating the value of s, because remember at the bottom it is I equal to 1. If there are m outputs, it's sum of e to the s
0 plus
I, right?
Yep, yep.
Where s is these. So if we call this s, then we call this s, it will become a total mess. So that's where I got.
Let's see.
It's because you didn't touch it for a while.
Yeah, just need to speak.
Okay, it should be back in a second. Okay. Okay, so anyway, to save time on it, as I had emailed it to you, I've already put it on the website, the derivation, and hopefully you guys have gone through and it made sense. So let me just very quickly show it to you. Okay, so anyway, so this picture is important. Okay, so let's see if I can make it bigger. Okay, so anyway, let's pretend we have 10 neurons, if we are doing our MNIST example. So each neuron computes the sum. So if we make a slightly better terminology. So what I did is small s will be used for the sum, the output of the sum unit, right? Then capital S over here will be basically the output of the softmax function. Okay, so but if you take a look at any one of these functions, for example, let's take a look at this softmax function, right? Internally, what will it be computing? It will be computing e raised power
S1.
So again, let's be consistent. Lowercase s1,
Yeah,
right? Over
Sum of
e raised power s0 plus e raised power s1 plus
so
s9, right? So as you can see, this unit is receiving an input from all the other units, right? So as far as gradients are concerned, if we were interested in finding, for example, delta 1, which is right over here in this neuron over here, which basically means we need to find partial s over, partial L over,
partial capital S.
over lowercase s1.
Oh yeah.
Correct? Okay, but now we have a lot of paths over here. As you can see, there's a path going from here to here, here to here, here to here, here to here. So we have to sum all of these gradients. Okay, and this is what I tried to show. Okay, so the second page was simply the derivative of the softmax function, independent of the delta computation. So here, we went through in the last lecture, so we came up with 2 rules. So here also, when I was giving you the last lecture, my terminology was not consistent. Okay, so over here, so once again, when we do the derivative of the softmax function, right? So again, capital S is the output, lowercase s is the input. So when we do the derivative, it has to be partial s over partial s. Okay, but because this is feeding to other units as well, so we have 2 cases, I equal to j, I not equal to j. So anyway, we came up with this in the last lecture. There was no confusion over here. There are 2 rules over here. If I is equal to j, it will come out to be si, 1 minus si, otherwise minus si sj. And as far as the delta computation is concerned, so that I explained in computing the delta I, and I just picked one example. And just like on the first page I showed you, so this is S1, there are many paths leading to that lowercase s1. So if we have to do the partial L over partial s1, okay, so it will be basically all of these will partial s1 over partial s0 over partial s1. all 10 of them need to be accumulated. Anyway, hopefully you guys went through it, now it will make more sense. For delta 1, it will come out to be minus y1 plus s1, or in general, this delta I will come out to be minus yi plus s of I, or in general, delta will be ys minus y. Okay, so that's the softmax function, right?
Professor, above the Sj term, Sj means the summation of all, where I is not equal to j, above, not equal. So while programming, so we can just be clear. Minus Si minus Sj. So Sj is nothing but sum of e raised to Sj, like all the terms upon that.
No. See, all this means is like, to give you, let's go to the picture over here. Okay, so for example, let's take a look at this one, right? Okay, for example, take a look at this part over here, this part. Okay, this will be partial S0 over partial S0, correct? So in this case, I is equal to j. So according to our equation, this will be equal to S0. 1 minus S0 will be the answer. Okay, but now let's go take a look at, for example, this part over here, right? So focus on this part. This is S1.
Yep.
So if we are computing partial S0 over partial S1, so that's the case where I is not equal to j. So what will be the answer of this?
Minus Si.
Minus S0 minus S0 of S1.
That is the previous one.
Right? Because those are the two cases we had developed. So there's no summation over there. And now if you go through the derivation of it, you'll see somewhere I'm using this, somewhere I'm using this, based on which partial are we looking at. Okay, so the bottom line is our result is extremely neat. Our result is that the delta in the softmax layer. So if this is our, remember we use softmax activation only in the last layer. Okay, so if this is our last layer, so all of these. Okay, so suppose this is going through a loss function L. Okay, so what would be the delta computations over here? According to our theory, this delta will be, so partial L over partial S will be what? That's what we call the delta, right?
Yeah.
Delta is the partial L up to this point. And if provided this is softmax, so what will be the answer for this?
Si minus.
S
Minus y. That's a big.
Sorry, S minus y.
Yeah.
So simply that's the answer. Okay.
That's right.
Then once we have the delta, then we can proceed the normal way. Okay, so now, okay, in your next assignment, I didn't ask you yet to program this. I know you had done it, but so your next assignment, you'll be programming the softmax. Okay, some of you have come and shown me your work, and it's some of you have done a very impressive, detailed analysis of the effect of the number of neurons in the hidden layer. Okay, you guys have also taken a look at different activation functions, but not the softmax, right? You guys have done sigmoid, ReLU, and what was the other one? Tanish. Okay. And also you played it with, you guys have played with the learning rate? Okay, one comment I'd like to make is, some of you discovered it, some of you came to me. When you guys were using ReLU, Okay, you might have noticed if you kept the learning rate of 0.1, it will do a terrible job.
Yeah.
Okay, so for ReLU, you have to decrease the learning rate to something like 0.01 or 0.005. Then you will see will give you very similar accuracy as the other cases. Okay. Okay. So. Okay. Let me put this on the notepad. Okay, so now, see, our goal is, like I said, by the time we are done with this course, I'd like you to know as much as, any top school in the country, maybe even better, okay? But I always believe that you cannot do anything advanced until your fundamentals are completely solid, okay? So as I've mentioned before, TensorFlow type libraries, there are a lot of interesting code out there. You can program, do something interesting, feel good. Oh yeah, you did it, but without really understanding what's going on inside, right? So we want to strike a balance, meaning we want to understand the fundamentals, then we also be able to do advanced. But if we spend too much time here, we wouldn't be able to do those things. So my goal is, before the break, meaning by the end of this lecture, I'd like you to have a complete solid idea of fundamentals so that then we can really focus on deep convolutional networks, deep recurrent networks, adversarial networks, reinforcement learning, and those type of things. After we have a good knowledge of those, then even if we take a look at the libraries, you'll be able to understand, okay, how is it working, right? Okay, so there's a couple of things left in our fundamental review, okay? One concept is how many layers to create. Okay, in the last assignment, all you did was just a single layer, okay? So how many inputs you guys had? 784 by 1. Remember, we did a 28 by 28 image, right? Then you fed it to either 100 neurons or 50, or you experimented with it, right? Then what did you go towards the output?
10 neurons.
10. And then you have the... Okay, so then we discussed that if we wanted to enhance the distinction between the 10 classes over here, what activation function should we use over here? Softmax, right? Okay. So now you have a very good idea of what softmax does. Intuitively, it's basically whatever the input it's getting, right? If the input is S2 or whatever, it's doing the exponential, and then further, in our case, 0 to 9 or whatever, e to the si, so that it becomes a probability distribution. Whichever output is being recognized, it will enhance it as high as it can. The others will become, very small, so that the sum of all of these will be what? 1, right? Okay, so anyway, not in the data set that I gave you, you may still not find a big difference in softmax, maybe a tiny bit, but some of the other data sets that we'll play with, you'll see there's a significant difference if there's quite a number of classes that are involved over there, right? Okay, so that's one issue. You'll be programming the softmax. And we've already talked about that you will do the delta computation as s minus y or y minus s, doesn't matter, depending on how we treat the cost function. But anyway, So then once we have the delta, we can go to the delta, we can compute all the weight gradients and so on. Everything will work fine. Okay. Now let's talk about, is one layer enough or should we have more than one layer? Okay. So we talked about it in the beginning of the course. And as I mentioned, according to the universal approximation theorem, if you are doing classification, meaning your goal is to recognize between one or the other, then basically one layer is enough. If you increase the number of neurons, you can do proper classification. Okay? But sometimes, rather than creating too many neurons over here, we do create layers so that we can do better regression. Okay, so that we can do better regression. So, and there are other cases where more than one layer is helpful, not from a classification point of view, but from learning features point of view, as you will see as we go along. So, whatever code you have developed, okay, what I'm trying to say, it needs to be converted to a form so that we can easily specify as many layers as we want. Okay. So in Python, you know, there's a concept of a list in square bracket. So the goal would be, and also we want to do it a little more object-oriented. The last code we wrote was, you know, just a terrible straight line code. So I'll help you with it. I understand not everybody here is coming from a good OOP background. So I'll give you my starting code as an option, meaning you can take it, enhance it, or you can modify your code to mimic the way I'm writing the code. So, and I'll show you the code in a second. So the way I've developed it is, we'll have a layer class. Okay. So it doesn't matter how many layers we want, how many neurons we want, right? So in this layer class, what kind of fields we would like to have? Okay, obviously number of neurons. You guys agree?
Yes.
For example, if it is the hidden layer, you may say 100 neurons in the constructor, or 10 neurons, or 50 neurons, right? So number of neurons, okay, what's the number of neurons in previous layer? Okay, why is that important to us?
So back propagation, right?
See, there's a weight matrix involved over here, right? So take a look over here as we go through the X input. We go through a weight. So what I want to do is, I want to encapsulate the neurons with its own weight matrix. So that appears on the input. What will be the size of this weight matrix? It will be the number of neurons times the number in the previous layer, right? Same thing over here. If this is 10, this is 100. If we indicate 10 neurons, but we tell it how many neurons are in the previous layer, or I should say not neurons, maybe just inputs in the previous layer, then we can easily create this, right? What other fields we want? Every neuron over here will have some kind of activation function. You guys agree? Okay, and in good programming, what we can do is we can create an enumeration. Okay, so how do we create an enumeration in Python? We create a class and specify, in a minute I'll show you the actual code. Okay, so we need the activation function. What other data we need? We need to hold on to the derivatives of the weights, sorry, gradient of the weights, so maybe rather than dw, let me call it grad w, right? Grad bias. Okay. What else? Do we also need to maintain delta in our neuron, right? Some we don't have to store it because it's really temporary calculation. So the actual output we will need to store whatever the output is, right? Okay, so anyway, so let's start with the layer class. And let me show you how I created it. Then gradually I'll show you how it's tied to the rest of the code. Okay, and I'll give you all of this code, so if you can just get an idea for right now. Okay, so anyway, as you can see, I have a class called layer. Okay, this is the constructor. In the constructor, what am I passing? How many neurons? So for example, if I wanted to create a layer with 100 neurons, I'll pass 100, right? Num neurons, previous layer. Once again, why is that important? So that we can decide on the size of the weight matrix, right? And last layer equal to false because softmax is only used in the last layer, right? So to distinguish, and I'll talk about the dropout in a few minutes. As first, let me just give you the overall structure of the code. And lastly, what kind of activation function we are using. So it could be sigmoid, it could be ReLU, it could be softmax, right? So basically, how do we create enumerations in Python? Very easy, all you do is create a class. So I added a class called activation type. And you just say sigmoid1, tan-h2, but in your code, you'll be using activation type dot sigmoid, activation type dot tan-h, and so on. Okay. Anyway, back to the layer class. Okay, so then I have some variables over here. So as you can, okay, again, don't worry about dropout for right now. Okay, delta, as you can see, what will be the size of the delta inside the neuron? If we have 100 neurons, it will be 100 by 1?
Yeah.
Correct? So does this make sense?
Yes.
Okay, what will be the size of the actual outputs?
Same number of
Same,
neurons.
right? Okay, the derivative of the activation function also, because if we have 100 neurons, right? The derivative over here will also be, there will be 100, if there are 100, 100 by 1. So deriv AF is the derivative of the activation function. Okay, and next thing, okay, basically initialization of the weights, just like before, uniform. Okay. By the way, the initialization of the weights affects the final result sometimes in a significant way. For example, if I show you over here, take a look at the line that I've commented out. Okay, you'll see it is 0.01 times some random number in this particular size, right? So essentially, are there any negative values that will be put in these weights over here? No, right? Everything is 0 and above in this particular case.
Yes.
Okay, so if I initialize the weights like this and run it, I'll get about 87% accuracy, around 87% accuracy, with the typical same things like you guys have done like 50 neurons in the hidden layer, ran it for 50 epochs, right? But if we do an initialization now, where did it go? Over here, between negative 0.1 and 0.1. Okay, so then it does a better job. It gives around 89 point something, depending upon what parameters you pick. So you can play with the initialization. And later on I'll talk about, there's Xavier initialization, there's another one called Glorot initialization, that based on some theory, they tend to perform better. So initialization is also very important in getting some kind of accuracy, right? Anyway, coming back to the layer, the rest of it is pretty easy. The weights, the biases, the gradients of the base and biases. This is related to dropouts, so don't worry about it right now until. So then basically inside the layer, I have the evaluate function, okay, which basically will do W times the input. Input data is the input plus B, right? However, now depending on the activation function, the actual output will be different. If the activation is sigmoid, then what will it be?
So call the function.
Call the sigmoid. So
Sigmoid.
basically what I did is later on over here in the same class, I wrote few tiny functions, sigmoid, tanh, relu, softmax, and so on, right? So anyway, the evaluate function basically has a lot of these cases. If it's tanh, what will be the output? If it's relu, what will be the output? And so on. Okay, so pretty straightforward as far as the layer class is concerned, right? So then think of a neural network. Doesn't matter how many layers it is. So layer represents the weights and these neurons and whatever data we need. So this we have encapsulated into the layer class. Okay, now if we have many layers, there is some set of weights, another set of neurons. Okay, so here's layer 1, layer 2, and so on. And let's say layer N. So what we want to do is encapsulate all of these into a class called network. So as you can see, the network class, inside it will be a list of layers. And also it will, it's the training is done on the network, right? So the network is what we will put the train method in it. Okay, so very briefly, let me show you the network class and you'll see it's pretty easy. Okay, so here's the